Dear participants, welcome to this course on industrial fermentation. One of the most influential professors in chemical engineering, Octave Levenspiel from Oregon State University in the United States, outlined in a 1988 publication the grand adventure of chemical reaction engineering. And this inspired us 30 years later to sketch what would be the grand adventure of biochemical reaction engineering, also known as industrial fermentation. This course will bring you up to speed in this research and engineering field in a series of topics related to bioproducts, renewable feedstocks, how they are converted in large-scale bioreactors or fermenters, and what is needed to design, operate and improve high-performance and robust fermentations. We will illustrate this with the key example of the monomer 1,3-propanediol produced from glucose and using bacteria at industrial scale. But also we'll highlight other examples that have born out of the global bioprocess industry. The grand adventure of biochemical reaction engineering is then the creation and development of new bioprocesses to make tomorrow's bioproducts. This should anyhow be cheaper, better, more sustainable, faster and less risky than today. One determining success factor will be to maximize the industrial performance in terms of titer, yield and productivity. As target for titer, we could take the Club of 200 as reference. Documented evidence that the product titer of at least 200 gram per liter has been accomplished. For rate or productivity, we have witnessed examples of 10 gram per liter per hour and conversion yield examples within 80% of the theoretical maximum governed by thermodynamics. The second main success factor is to do this in a robust way without surprises. It is good to distinguish two product categories, simple and more complex molecules. The simple ones will act as commodities, and the complex ones are more the specialties. They serve different markets with different needs, and the fermentation solutions will be largely different, as will be revealed in this course. Further important is to realize that a great idea and results in the lab do not guarantee commercial success. Many promising avenues have ended and will continue to end in the so-called innovation valley of death. In this course we hope to give you insights and instruments to cross this valley and achieve a higher rate of business success. The essence and mission of biochemical reaction engineering is then to come up with new and more efficient bioprocesses to make new or better bioproducts. And this is a two-step affair. First, we need to do the dream work, the conceptual design of the process and product. And only when this is done properly and with reasonable effort, then it is time to make it real. Develop the process and engineer the factory. The dream work thus precedes the teamwork. And the rule is that better upfront thinking will unavoidably result in a faster and better outcome. The industrial fermenter or bioreactor is the heart of the bioprocess. There the renewable feedstock is converted into the desired bioproduct with the help of microorganisms present in the fermentation broth, tiny cell factories that are the masters of efficient conversion. Further needed is energy for mixing and often a gas like air, methane or carbon monoxide. Also, gaseous compounds such as CO2 and unused gas will leave the reactor. We as engineers should maximize the speed of conversion whilst maintaining the high efficiency or selectivity. An important rule, or perhaps better type as design philosophy, is then to begin with the end in mind. The design of the fermentation process in the lab should be done from a perspective of execution at industrial scale. And this applies to both the medium throughput research and development stage as the high-throughput screening stage. Maintaining as much as possible the same environment of the cells in either scale, industrial, lab or screening will secure similar performance and minimize surprises upon scale-up. The begin with the end in mind philosophy was first presented by the author Stephen Covey, and we have adopted it for our purpose with the following recipe. Begin with the product. Its required amounts to be made, its properties and purity specifications. Then select the best feedstock for the product based on thermodynamics and verify if the conversion produces or consumes energy. And if the first is true, then a very large-scale anaerobic process might be feasible, which will be by far the most economic. If not, then there will be restriction in volume and cost, and economics and market deployment potential need to be carefully judged. The next step is then to select or develop the best microorganism for the process. Not the other way around, which is mostly the common practice today, but gives scalability issues. Nowadays, there are powerful strain improvement and evolution techniques available to tailor the microorganism to the task. Finally, the process should be scaled down to the lab and optimized there before scaling up to the industrial factory. This then presents an integrated approach to industrial fermentation development. Operation in the factory, with limited measurements to satisfy minimum control needs, should be done jointly by factory and research experts. Optimization can be done either online in the factory or offline in the lab, where proper scale down of the cellular environment from the factory to the lab will minimize the risks of misalignment and scale up issues later on. And even when there is limited information from the industrial scale, we advocate this end-in-mind approach will be feasible and the best way to save scale up. The grand adventure in front of us then is to secure fast, environmentally sustainable and low-cost development and commercialization of tomorrow's byproducts with minimal risks, failures and surprises upon scale-up. Conceptual design is highly recommended, where dream work precedes the teamwork. And this is often violated in academic education programs, where quickly one begins to deploy the engineering toolbox, the how, without having thoroughly scrutinized the available design options, or the what. The process of innovation should begin with purpose and end application in mind, and an integrated approach to research, design, development, scale down, and commercialization, scale up, is essential for success. I wish you an enjoyable adventure.